Okay, welcome back. Today we're talking about factoring polynomials. If you remember distribution, right? We're going to start here just for a second. If I have it, let's say a 3 multiplied by nx minus 5, right? I can distribute that 3 through. And then this is equal to 3x minus 15. And this is one direction of the distribution, right? I'm taking this, distributing it into there, and I get this. But I can go the other way. I can say, hey, 3x and 15 are both divisible by 3. And so essentially, I'm undistributing that 3 and saying, hey, this 3x minus 15 might have started as a 3 sitting out here multiplied into an x minus 5, right? So that's the general idea. That's what we're looking at here that's what factoring means. It's kind of undoing this sort of distribution. And we'll talk about some of the ways to factor these polynomials. But let's take a look at another example here. Let's say I have something bigger. Let's say I have 3x squared multiplied by, let's say, 5x plus 9. Well, that, when I distribute, becomes 15x to the third plus 27x squared. And again, we can look at the right-hand side of this and say, what can I essentially pull out and write over here as a product? And that's what factoring is taking something and turning it into the product of other things, right? And that's the biggest thing that I can pull out here is a 3x squared, because 5x and 9 have nothing else that will divide evenly. And so to look at this and say, what can I pull out? The biggest thing that I can pull out from over here is that 3x squared. And so on the right, if I were started with this, the factorization would be what's on the left, right? So when I factor, let's take a look at perhaps something easy like this, 8x squared. Minus 20x, or sorry, to the third. I'm just using the example from the book here. X squared, right? What can I pull out of here? Well, the biggest thing that I could pull out is a 4, right? If I say that I could have started with a distribution of a 4 through a 2 and a 5, and I can actually have an x squared that comes out with this as well. And I'm left with a 2x minus 5, right? And so if I started with what's on the right here, this 4x squared times 2x, that would give me the 8x to the third. 4x squared times minus 5 gives me the negative 20x squared, right? So that's an example of turning it into this right-hand side. And I got this 2x and this 5 by dividing. Right? So essentially what I'm saying is if I take this 8x to the third and this 20x to the second, I'm looking for the greatest factor, the greatest common factor that I can, the biggest number, the biggest expression that I can divide both of them by so that I can bring it out here. Because that division is essentially the inverse operation of the multiplication for the distribution. Right? So that's the key, is that we want to be able to divide all of our terms by the same thing. So if I look at something like, say, 6x to the fifth plus 8x to the fourth plus 10x to the third, right? And I take this and I divide it all by, let's say, 2x to the third. Well, if I'm taking this and dividing it by a single term, I can actually just take each individual one of these things and divide it separately. Because this division is essentially just a rational expression. Right, it's all of that over 2x to the third. But again, each of these individually can be placed over 2x to the third because it's just a monomial. So I can write it as this, 6x to the 5th over 2x to the 3rd plus 8x to the 4th over 2x to the 3rd plus 10x to the 3rd over 2x to the 3rd. Right? Which means I can just divide each one of them individually. And so 6 divided by 2 is 3. I have x to the 5th over x to the 3rd. That's going to leave me with x squared. 5 minus 3. Plus 8 divided by 2 is 4. X to the 4th over x to the 3rd is just an x. 10 over 2 is 5. X to the 3rd over x to the 3rd cancels out. And so the result of the division is 3x squared plus 4x plus 5. Which means that I could, since all of these are divisible by 2x to the 3rd, I could factor that out from here. And that's essentially where we're going with this. Let's take a look at another one. Let's say that expression divided by 4x to the 3rd. Oh yeah, I don't have to rewrite this every time to know that I can just treat each of these individually. So I can take 8x to the 4th and divide it by 4x to the 3rd, and then move on to 12x to the 3rd divided by 4x to the 3rd. What happened with my numbering system? Changing it just a little bit, sorry about that. I want 6th, 5th, 4th, and 3rd powers here, but I can just go term by term now. So I would take 8 divided by 4 is 2, and then the x's, I have x to the 6th over x to the 3rd, that leaves me with x to the 3rd. And then I move on to the next one. 12x to the 5th divided by 4x to the 3rd, 12 divided by 4 is 3, x to the 5th over an x to the 3rd is x to the 2nd. 16 over 4 is 4, and then I'm left with an x. And then 64 divided by 4 is 16. The x to the 3rds cancel out, and I've got that. I can check to see if that's the biggest possible thing that I could have factored out, because my numbers, 2, 3, 4, and 16, have no common factors, right? 2 is only divisible by 1 and 2. 3 is divisible by 1 and 3. So already I can't divide anything evenly that would go all the way through all of these. And that's it. That's my value. All right. So let's try and factor. All right. If I have some, let's do this one. Let's go, not a 7. That's, looks like, all right, I'm on the screen still. I have a tendency to get higher as I write to the right, but looks like it's mostly on screen still. There we go. So if is that worse? Sorry, maybe it is, I don't know. Okay, so I want to factor this. I want to factor the greatest common factor, which means I'm going to look at each of these and pull out the biggest possible thing that I can. Well, I have 6, 18, and 15, so the biggest number that all of these things are divisible by is a 3, right? 6 is divisible by 3, 18 is divisible by 3, 15 is divisible by 3, and that's it. That's the biggest thing that I can find to factor out. So I can factor it, but I can also take out x's. There's x to the 5th, x to the 4th, and x to the 3rd, so each of these terms has at least an x to the 3rd, and so that is part of my greatest factor as well. I could divide x to the 3rd through all of these, right? And so I will. I'll divide 6x to the 5th by 3x to the 3rd. That leaves me with 2x squared. 18 divided by 3 is 6. X to the 4th over an x to the 3rd leaves me with an x. And then 15 divided by 3 is 5. X to the third over x to the third leaves me with just that 5. And this is my factored form. Right? And so we would call this is the greatest common factor, oftentimes abbreviated GCF, right? And then the resultant from that factorization over here, and the product of those two things is the factored form. Alright, if I want to factor this, again I'm looking for the greatest common factor, the greatest thing that I can pull out, the biggest coefficient, the biggest number of x's or y's or z's or whatever you have, right? 8 and 12 are both divisible by 4, and so is 20, right? And so 4 is the biggest thing that I can factor out, right? And if you're not sure, we're going to factor it and then look at the result and make sure that 4 is correct, right? But I can also pull out x to the 4th. And so 8 divided by 4 is 2. X to the 7th over x to the 4th leaves me with x to the 3rd. 12 divided by 4 is 3. X to the 5th over an x to the 4th leaves me with just an x. Minus 20 divided by 4 is 5. X to the 4th over the x to the 4th. No more x's. And looking at my result, I have a 2, a 3, and a negative 5. There's nothing else I could have pulled out of there. So this is it. That's the greatest common factor. And this is my factored form. Good. All right. Let's look at something a little ugly. Let's look at 6x to the 4th y minus 6x to the 3rd y squared plus 12x squared y squared. It may look a little bit ugly, but it's not any more difficult. The greatest thing that I can factor out is a 6, because I can't factor out more than a 6 when one of these numbers is a 6. 12 is divisible by 6, so they're all divisible by 6. The only restriction on my variables is the smallest one, right? So I have y here, y squared, y squared. I can only divide out as many y's as my smallest term has. And this has one y, and so I can pull out a y. As far as the x's, my smallest power of x is x squared, so I'm going to pull out 6x squared y. Because each of these has at least 2 y's, and each of these has at least each of these has at least 2 x's and at least 1 y. So what do I get when I divide this? Well, I just do the coefficients. 6 divided by 6 is 1. X to the 4th over x squared will leave me with x squared. Y over y goes away, so the first is just x squared. Minus 6 over 6 is 1. X to the 3rd over x squared leaves me with an x. Y squared over a y leaves me with a y. Plus 12 over 6 leaves me with 2. X squared over x squared, the x's are gone, but I have a y squared over a y, that leaves me with a y. And as I, again, look at the result here after the division, there's no x in this term, so I couldn't have pulled out any more x's. There's no y in this term, so I couldn't have pulled out any more y's. And then my numbers, 1, 1, and 2, they have nothing that I could have divided by, so that's it. That's my greatest common factor and the resultant factorization. Okay. So sometimes you might see things like in fact, let me throw in, let me just call this a y for now. But each of these I can treat like terms, right? I have 4 multiplied by this x plus 3. I have this y multiplied by x plus 3. If I were to have come across something that said, say, 4w minus y times w, if each of them has a w, that can be factored out. And so I can say that this is w times 4, the w cancels out here, minus y times, and the w cancels out here. And so it ends up as that w on the outside here multiplied by the result, right? But this problem is this problem. W is just in place of x plus 3, right? So if I treat this w like what it was meant to be, that x plus 3, then I've still factored, right? If this x plus 3 appears as a factor in both of these terms, I can pull it out, and it's just like dividing all of this by x plus 3. Divide the first term by x plus 3, it cancels out and leaves me with a 4. Divide the second by an x plus 3, it cancels out and leaves me with a y, and a minus between the two. And so I can factor not just single terms, right? I can factor out a binomial, or I can factor out a trinomial. If there's the same polynomial here and here, I can factor those out, right? So let's see that in action. I might have, say, 2 times x plus 5 minus w times x plus 5. And again, because I have an x plus 5 both here and here, I can treat that as my factor. So it comes out, and it gets multiplied by what's left after that leaves, so that's a 2 minus a w. And I factored it. Might get bigger, right? I might have something like, say, 5 times x squared plus 3x minus 2 minus x times x squared plus 3x minus 2. As long as I have the same polynomial, right, I can pull that out and factor it. This polynomial comes out as x squared plus 3x minus 2. Again, just divide it from both terms. If I divide it here, it just cancels out and leaves me with a 5. Minus, if I divide it here, it just cancels out and leaves me with the x. And I'm factored. Good. And we'll see that pop up when we get a little bit more into factoring. But let's move on here to polynomials that look like this. In fact, let's start here. If I have these two binomials multiplied, I would FOIL them together, and I would get x squared minus 4x plus 3x, and then minus 12. And I can simplify, of course. This becomes x squared minus x minus 12. Right? But if I can go this direction with this math, then I can go the other direction with it, right? And it's kind of a nifty trick, because if you're given this right-hand side, sometimes it's not that easy to see that it's going to turn into this left-hand side as a factored form. But the trick is to then try to recognize what middle two terms would have simplified to give us this middle term here, right? And so let's talk about that, and let's talk about how to get that manipulation down. Let's say I have, let's do this, x squared plus 7x plus 12. And we want to factor this into two binomials, right? Well, we can do that here. So let's take a look and figure out what this what this 7x should have come from. And to do that, I'm always going to look at this last number, right? As long as the number in front is 1, this last number is all I need. So I'm going to take that number off to the side and figure out the factor pairs of it, the two numbers that multiply to give you 12. For example, 1 and 12 is a factor pair. 2 and 6 is a factor pair. 3 and 4 is a factor pair. And that's all of them. And I know that's all of them because I started in order. 1, 2, 3. And then 4 is here. I know 5 isn't here because 5 is between 4 and 6. And so if it were here on this list, it would have a factor pair between 2 and 3. But there isn't an integer between 2 and 3. So that's it. I can always start at 1 and just keep going until the two numbers down at the bottom have no numbers between them that are part of the factor pairs, and that's how I know I'm done. Right? But I want to pick out the two numbers that will give me that middle. So that is to say, those two, 3 and 4. Right? And so I'm going to replace this middle term. Instead of plus 7x, I'm going to have it plus 3x and plus 4x. So it's the same thing, I've just rewritten 7x as a 3x and a 4x, and then I'll just group this. First two go together, second two go together, and I can factor just a part of this. If I factor the x squared plus 3x, the only thing I can pull out is an x, but I can pull out an x. And that leaves me with x plus 3. On the right hand side, the only thing I can factor out of there is a 4, so if I factor out a 4, the 4 cancels out, leaves me with an x. 12 divided by 4 is 3, and look at that, just like magic, I have an x plus 3 here, and an x plus 3 there. So like those last problems, I can factor out the x plus 3. And what am I left with but the x plus 4? And you can check this by refoiling this together, but this is my solution. That is the factored form of this x squared plus 7x plus 12. And that works every time. And this, I did every step along the way. You don't have to do that, right? It's not a coincidence that I got a 3 and a 4 in my final answer when I separate it into a 3 and a 4 here, right? So I can always, as long as that first number, that first term, that x squared is a 1 in front of it, I can always just say, hey, it's these guys and jump straight to here. I don't have to do these two middle lines. So let's see that in action here. With this, perhaps, right? Again, I'm just going to jump to this 18 and find its factor pairs. 1 and 18, I'm always going to start with 1. 18 is divisible by 2, so that is 2 and 9. It's divisible by 3, that gives me 3 and 6. It's not divisible by 4, it's not divisible by 5, so I know I'm done, because the next number 6 is here already, right? So it's a pretty quick, as long as you go through that method, it's pretty quick to say, hey, this is it, that's all my possible values, right? How do I get a 9 out of a 3 and a 6? They're both positive, so that means that this is going to end up being a plus 3, x plus 6, and I'm done. That's it. Done. I can verify this because x times x will give me the x squared. I'll get a 6x and a 3x that combine to give me the 9x, and then an 18 out of that. All right, let's see another one. If we throw some minuses in here, it just changes things ever so slightly, not a lot. But now I'm looking for factor pairs of negative 14. So I'm going to ignore the negative while I create the factor pairs, and then I'll figure out what the negative has to be to make this work after I've chosen my pairs. well, in order to choose my pairs. So factors of 14, well, 1 and 14, 2 and 7, and that's it. 14 is not divisible by 3, 4, 5, or 6. I'm done, right? So how do I get a negative 5? Well, these numbers have to multiply to this number, the big negative 14, and they also have to combine to negative 5. And so I can do that if I allow, in this pair, if I allow the 7 to be negative. Because negative 7 times 2 is negative 14. Negative 7 plus 2 is negative 5. So those are my guys, right? So I'm going to write this as x. The 2 is positive, so it's x plus 2. The 7 is negative, so it's x minus 7. And that's it. That's my answer. Let's verify this one, though. Let's just FOIL this together just to make sure. X times x is x squared. X times negative 7 is minus 7x plus 2x minus 14. And then, of course, you can see this simplifies, and we get the original thing back, right? And therefore, we know that this is correct. Let's look at, let's do this one. X squared minus 17x plus 60. So far our factor pairs have been a short list, right? But now I have to find factor pairs of 60. This will probably be a little bit bigger, right? But it's still not terrible. Again, if I start at 1 and 1 is always there, 1 in the number itself should always be on your list. If I just start at 1 and then go to 2 and 3 and 4, you'll see how fast this list kind of deteriorates all of your options. Well, 1 in 60, right? There's 58 other numbers that could be in here. But the next possible one here is 2 and 30. And I'm already halfway done with all of the numbers between 1 and 60, right? Because any number between 30 and 60, if it appears on this list, would have a factor pair between 1 and 2. But again, there's no integers, so I don't have to check 31 through 59. They're in the garbage. I don't care about them. So I'm already halfway there. 60 is divisible by 3. That gives me 20. That's another huge chunk of numbers I don't have to care about. It's divisible by 4 and 15, so it's a pretty small list now between 4 and 15. It's divisible by 5, and that is 12. It's divisible by 6, which is 10. As you get further down the list, you start hacking away smaller and smaller chunks, right? But it's not divisible by 7, it's not divisible by 8, and it's not divisible by 9, so I'm done. Because here's 10, that's all of them. Now I have to combine to be a negative 17, right? And so if I look at these guys right here, and I call them both negative, negative 12 and negative 5 combine to be negative 17, and they still multiply to give me a positive 60, right? So those are my two. And therefore this turns out to be x minus 5 times x minus 12. And again, you can verify that, but you can see minus 5x and negative 12x will combine to give you negative 17x. The negative 5 times the negative 12 will multiply to give you that 60 positive. And we're done. All right. We'll see some other methods. Well, you will see some other methods in the future, especially when you start not having a 1 in front of there, but that's a lesson for another day. Thank you guys, and I'll see you next time.